Oops.
All
right, let's pick things up before we left off last time. Greggy, were you there?
Brady's here.
Oh, okay, good. Good, I don't see you. For some reason, I've got Corpus, picture of an empty room in front of me today. When we left off last time, we were dealing with the finite well. So I want to go back and finish up the discussion that I had on the finite well and do a little bit of problems and then move over into the notes that I sent you on Sunday. In particular, we talked about this fact that this solution to the energy levels was not pretty. That solving to try to find E requires you to work this equation. And to solve that equation for the energy levels, and that equation is obviously not one that I'd really like to work. So what I did was difficult to do by hand. You can replace the energy with some fraction of the well. Okay, so the well, if you're trapped, you're bound. So the energy of your particle has to be less than the walls of the well. But the well's not infinite. So you don't get that nice little simple formula. So instead, I've replaced the energy with a fraction of the height of the well. And I'm looking for that eta. And you put that all in, and you still look here, and it's still an ugly looking little equation. So the problem is how to find those etas. If you could plot this side of the equation, and you plotted -1 on the other side of the equation, every place those two things crossed would be an answer. That'd be a graphical solution to that problem. And so in the next page, I had some diagrams that I'd done, and I didn't do it with a fancy computer program. It's been a long time, and my compiler C that I used to use is actually in DOS. So I don't use it to write in Java or anything else. I just used a spreadsheet. So I basically plugged in a spreadsheet, and I said, hey, plot me the numerator, which is this dashed line, plot me the denominator so I could look at it, which is the top line, and then plot me the ratio of that, which is my left-hand side, which is this curve here. Wherever that curve passes -1, which is right about there, I can go up and read eta, multiply it by your barrier, and I have the energy level. Now this one's for a very shallow well, and I'm going to show you that. So let me go over to my computer, and I'll show you my little program. And I think I sent this out, but if I didn't, I'll send you a copy. So as an input, you have to tell it the height of the wall. It knows about HC, and it knows about this being an electron, so you have to tell it about the energy of the particle. And then it knows about the well's width. So basically, I've just told it the same things a person would tell me in a homework problem. How tall is the well? How wide is the well? What's the particle trapped inside the well? And then I went through and I calculated for eta, for the numerator and denominator. And then finally, this thing here is the left-hand side. So the only place the answer works is when the left-hand side is -1. So when eta is 0.02, which would be 0.02 times 4 EV, right? So that'd be 8 divided by 100, so 0.08. This does not match up with -1. That's not a solution to the problem. And then I just went and I had this whole column, and I just plotted that on the Y, and I plotted this on the X. And I got this chart that I crafted for you. So coming along here, see it was up here about 0.8, and eventually it comes down, 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 down. It hits right about here. And you can go up and read that eta, or you can go back to the spreadsheet and see where it passed -1. And from that, I was able to get the value, and I actually gave you the number for that energy level. Now, this kind of actually guy looks almost like a deuteron. Deuterons are very interesting because protons and neutrons inside a nucleus have no excited states. They have one state, and that one state is the ground state. And if you try to give it any energy and excite it, it dissociates. It's no longer a deuteron. So it is impossible to study the nuclear force by studying the deuteron, even though that's what you want to do. It only has the nuclear force. There's no electrical force because the neutron is neutral. So you would think that you could just give it a little bit of energy like a photon, see what excited state it went to, and then you could determine all the energy levels. Can't do it. Not unless you give it any energy to associate. So therefore you have to have at least 2 neutrons and a proton. That's called a 3-body process. It's never been solved uniquely in mathematics. Okay.
A deuteron is just a proton and a neutron.
Proton, neutron, 2 bodies. That's it. Like you did with the hydrogen atom. 1 proton, 1 electron. Study the nature of the forces by giving it energy and watching it move between the levels. You can't do the same process in nuclear physics. It's one of the great difficulties in nuclear physics. So, that's a shallow well. And the reason the deuteron doesn't have excited states, it's got a shallow well. One way you could represent it is a 3-dimensional finite well. And that's what's done actually in nuclear physics texts. I also did another one where I did a deeper well. And in this case, I have a well that's a little bit, let's see if this is the right one. Yeah. So this well is 40 electron volts deep, not 4. It's a much deeper well. So because it's much deeper, it can, and it's therefore moving toward the infinite well, you get more solutions. So when you plot this, again, I just put in the width of the well and the depth of the well, and then I plotted it. Here's my value, and the value crosses -1 right here. So it's got an energy level of about 0.12, 0.13. You multiply 0.13 times 40, and you have the energy. So that's one solution to the problem. Now, this line here in the notes, that's an artifact. Because what happens is this thing goes to -infinity. And then it comes back here from +infinity. I told Excel to draw lines between the data points. So when it's down here at -infinity, it tries to draw a straight line up to +infinity. So this line is not actually part of the equation. It should be an asymptote there. Excel doesn't handle asymptotes like that. So this line is fake. There is no line here. So the fact it crosses right there, that's not a solution. Just the curves are the solution. So here's the next one. That's an asymptote. Here's one. Here's the next curve. So there's an excited state. And that would be the first excited state. You can get its energy. Then here'd be another one. You get the second excited state. And another one, the third excited state. And another one, you can get the fourth excited state. You cannot exceed 100% because then it's not bound. The energy is greater than the well. The particle comes out. So there's a set of bound states. They're not evenly spaced, and they don't follow some nice formula like n squared. That's solving it exactly. All right? Use some sort of a computer. Write yourself a code. Sit down and write a C thing and solve the problem. Probably not doing this sucker by hand. All right? So, depends on how you look at it. The good fact is you need to be able to solve a problem like this. That's fair game in the real world. That's a real world problem. They want the problem solved. They didn't say approximate it. They say get me the answer, build me the device. You can't solve real world problems you're not going to use. All right? On the other hand, you know you're not going to get that problem on test. Because you can't do it by hand. I guess I could make you write a code like they used to when I was a student, and you had to write a code for your pocket calculator and turn it in. And that was graded. You may spend an hour writing that pocket code. That's not an uncommon thing for graduate school. But you're not going to get, obviously, an in-class exam like that. So what will you get? You get questions about things close to the infinite well or about a qualitative shape, but you're not going to get about a numerical problem. All right, with that, let's let's talk about what we can draw and can do if we know something about. Well, the wave functions are also can be quite ugly for the finite well. And in your notes I wrote them. You can simplify them, but you end up with some sort of in the well of a sine and a cosine, but it's not going to truncate. Because it's not going to go to zero, you're not going to lose one of those terms. You're going to depend upon the wave number inside the well and the decay constant that's going outside the well. And then on the outside, once you get beyond that, depending on your wave function, you can also have it dropping off. Notice, aren't those sines and cosines? They're not have a variable x in them. They're constants. But the constants depend on the length of the well. So this is some constant times the decaying exponential. Again, I don't think you probably want to graph that. All right, not quantitatively, where you've got to get a number. Oh, and you still need to integrate all this to find the normalization constant. I guess I could have summed down.
Why is it
Have
different?
the fun of trying to actually do that, huh?
Why is it different before the well than it is after the well?
Because at the well, you have a very nice fact that it happens to be at x equals 0. If you had taken this not to be a place where the well starts at 0, but the symmetric well, where it goes from like minus L over 2, then when you were solving for those coefficients, you wouldn't be putting in 0 for x. When you put in 0 for instance, let's say you put in sine for x. Well, that's 0. Cosine of 0 is 1. You don't have any sines or cosines. But when you put in L for x, you get sine of KL, cosine of KL. That depends on k's value. These are not going to be 0, and they're not going to be 1. So 0 is a very nice place to put your axes because it makes the math look simpler. Unfortunately, both sides of the well can't be at 0. So one side will always have some ugly looking stuff in the coefficients, and there's no way to get around that. You got to deal with the math. That's why we take math classes. I'm not going to try to work through. I gave you plenty of stuff for you to work through all the math. You should be able to do so. But I think you should be able to also, and this is something you can be tested, graphically draw very quickly a rough sketch of what this thing is going to look like. So, for instance, somebody could ask you to write like the first allowed energy state or the second allowed energy state. So let's say that somebody asked me to write the second allowed energy state. That second allowed state should look something kind of like what the particle in a box looks like if it had infinite well. So if it had an infinite height, how many humps would I expect to have in the infinite well? For the first excited state?
1.
He says 1. How many humps then would you have for the ground state?
Oh. 2. I mean, for the ground state, 1.
3.
Ground state 1, so the first excited state would have
2.
2. So the n of the well, of the infinite well, is the number of humps. The same thing has got to be true of the finite well. So if I was drawing the ground state here, right, let's just do that first. If I did the ground state here, I was doing the ground state. There's X. So there's 0 and there's L. I expect something like that, kind of a hump. Symmetric. My graph's not perfect. If this was an infinite well, I would expect this to go to here. It would be at 0, and you have no probability of being inside. The only thing I'd expect to be different about the finite well is it'll have an exponential tail. That would be the n equal 1 state. Now that's not a mathematically rigorous thing, but I can get you a lot of information about that. There's one maximum in the problem, in the well. There are no points where it's minimum in the well. The average location of the well of the particle is L over 2. That's the expectation value if you were to try to measure it. That's the most average place. I don't have to have the exact solution to the problem to get a lot of information about the problem. Try to get exact information, it's going to take a lot of math skill. Depends on how important the answer is. Has the answer got to be to 1 part in 10,000, or has the answer just got to be roughly the answer? Is that all I need to know to solve my problem? If the second is the case, this is good enough. If the first is the case, I get to get back to my computer and I get to apply the full mathematical treatment of the skills that I got going through school. All right? If I was to find the probability, this is the wave function, I'm going to square that probability. What's that going to do? What's going to peak this thing more? Where's it most probable? It's most probable at L over 2, by symmetry. That's the most likely place to find the electron. Where's the average place to find the electron? Well, that means that I have to sum this all up, but I can tell you that by symmetry as well. The average is L over 2, so the average and most probable are in the same place. So if I was to make a measurement, then the answer I'd most likely get is L over 2. And if I took 10,000 electrons and I measured all of their positions, and I might get different values, some would be over here and some would be over here, some would be even over here, outside the well, some would be over here. If I added up all those things and looked at the average, I'd find it's L over 2 again. If you do the next one, the one I was going to start with, it should look like the particle in a box again, except the particle in a box this time, instead of coming like this, start a little high, we're going to end up a little low. Should have 2 humps. This is the n equal 2 state. N tells you the number of humps. This is going to go down. This is going to go back exponentially to the axis. Square that to find the probability. We'll do that in blue. This is going to go down quicker. Two humps, very fast fall because you got an exponential square. We'll come back to this because I want to use this fact that it falls off so fast as a way to do an approximation of this with the infinite well, which is what the book does in this chapter. These peaks, if I've drawn them right, should be the same height. So where's the most probable place to find it this time? L over 4, 3L over 4. What number will I never get? L over 2. You will never measure L over 2. Never. What's the average location of the electron? L over 2. That's the macroscopic value. That's what you would get if you're measuring classical physics involved in lots of electrons. But in fact, no electron will ever give you that value in any experiments. That is a minimum probability play.
So if that was to be like n over 4,
there would be 4 peaks.
Okay.
In the system, and there would be 3 minimums. The number of minimums is n minus 1, the number of peaks. So if you told me you want the 9th excited state, which is n equal 10, I will tell you right now, there are 10 maximums, and there are 9 minimums in the location, and the average will still be L over 2. Because that's the symmetry of this particular problem. And I do not have to do advanced math to do that. So, drawing a probability distribution for any problem, being able to write what the wave functions look like graphically, is fair game. That I can ask a lot of questions in a 2 or 3 hour test. I can ask you to do lots of wave functions. Make sure that you understand how we go about looking at something and knowing the wave functions. And in particular, make sure you know the ones that are in the book, because those are the easiest ones. Those are the only ones you can do and kind of use as a guide for a real world problem that you can't work without a supercomputer. All right? So they're like the obvious simple problem of, oh yeah, we're going to do the falling ball problem. We're not going to consider air friction. Because when you start considering ballistics, the problem gets really hard. Okay? So you must be able to do the simple kinematic problems, because it's the first approximation. These are the first approximations, every one in the book. If you can't do them, you have no chance of doing a real world problem in electronics or such, where solid state is much more complicated. All right. By the way, some thoughts about this little guy. This guy has some probability of getting into the well. That's kind of weird. How the hell does he get in the well? He doesn't have enough energy to get in the well. One way to look at this is that if you don't have as much energy as potential, then you're going to have negative kinetic. That doesn't kind of make sense. But remember, this conservation of energy stuff is a classical idea in a way. It's an idea that we measure and have never found to ever be violated. But measurement means we have to be able to measure it. And the uncertainty principle says that you can't know that delta E is 0 unless that time was infinite. So for a short period of time, you can borrow a short amount of energy, violate conservation of energy, and there's no way experimentally for you ever to be able to prove that. So if you don't need to borrow very much, if the wall's not too high, you can think of it as borrowing it for quite a long time, and you should be able to expect that you can penetrate quite a distance. On the other hand, if the wall is infinitely high, and you need to borrow an infinite amount of energy, you can borrow it for no time. That's why you don't have any penetration. That's one way to look at how you get an evanescent wave into a barrier. All right. All right, let's see. I think I had a problem on the finite well in your test your knowledge stuff. So problem 2 of the test your knowledge question says you have an electron trapped in a finite well of length L and height V naught. Before I draw it, I want you to draw a qualitative sketch for the wave function of the third excited state. What does that mean in terms of n? 4. A lot of you guys botched that on the test. Yes. So we're talking about the n equal 4 state. So I want a wave function here. See if you can draw me the wave function for the fourth state. Once you finish that, I want you to draw me the probability distribution. Then the third thing I asked for is what's the expectation value for this state. See if you can get me those. I'll give you, say, I don't know, a minute and a half. Should be plenty of time to make a rough sketch. You got about 30 seconds. All right, let's try the first one. How many humps? 4, all right, agree with that. You know this guy's gonna come like this. By the way, how do I know it's on top? I don't know it's on top. It could be underneath. Right? Only the square has any meaning anyway. So whether it's like this or it's like that doesn't matter. I just tend to be a person who draws on top first. All right, so don't make a bit of difference when you square them. So you could say it's like this. I always prefer to start like this. And then I need 4 humps. There's 2, there's 3, there's 4. All right. That's L. And then the exponential decay on the other side. Should have a wave function look something like that. So, how many of you actually have something that looks like that? All right, great. So, pretty much everybody got that. Then all you got to do then is square that. So now these humps on the bottom are all going to come on top, and they'll get peaked because you get the square of this number is going to get big, and the square of that number is still going to be small. In fact, if it's less than 1, it's going to be even smaller. So these just kind of get narrowed, and they kind of get raised up. So you're going to get something like this. Two, 3, 4, and then something like that. So, how many of you got something that looks like that? All right, so good. So, easy points. All right, sure, a lot easier than solving differential equations. We don't have plenty of those to solve. Okay, and spherical coordinates and so forth. I really hate to give away points like this. But there's a lot of usefulness in this because I can tell you lots of things. For instance, okay, that's right in the middle. That's got to be L over 2. That means that's got to be L over 4. That means that's got to be 3L over 4. That's halfway between those two. So I can tell you where all the peaks are. I don't have to do any advanced math. Just by symmetry and looking at the problem, I can tell you where things are. So I can tell you what the most likely probability place to get. I can tell you what the least likely probability to get. I can't tell you if this happens to be 4%. That's the problem. And I can't tell you, some other things, but I can tell you, for instance, the probability to get this thing, say, right in here. Well, that's about, there's a little bit over here. Okay, from here to here, it's about the same as in here. It's about the same as in here. It's about the same as in here. So this peak in here has about a quarter. Between L over 2 and 3L over 4, at least an approximation. The graph has a lot of information if you learn to read the graph. And you don't have to do advanced math to do it. What's the average location? L over 2. By symmetry. I don't need to do, now, feel free to go ahead and work this problem like this. Feel free. You just put in all those functions that I had and break that into 3 intervals and work them off. Maybe you'll be happy with it. You mastered your integration. All right. But there's no need to do that. That'd be a stupid thing to do because the symmetry of the system tells you the answer. It's not to say you shouldn't be able to do this. You got to be able to do this. But there's no reason to use a sledgehammer to get through a door when all you got to do is turn the knob. All right? So do some thinking before you just jump off. This is why you should draw things. You're picture-oriented animals. Take a good drawing. If you can't draw it, you don't understand it. If you don't understand it, you don't know what you're doing with the map. All right? See if you can't draw the thing before you just jump off the cliff. There was another problem in that set, which is a little bit harder. And it says, approximate the energy of an electron trapped in a third-sided state of a finite square well with a potential height of 3.6 electron volts and width of 0.25 nanometers. Okay, now one way to try to do that is to try to use my little computer program, right, and try to get it. Another way is to try to approximate this in some way as an infinite well. And the answer to the infinite well is kind of told to you in our previous graph. So we'll come back to this in just a second. You can write it down if you want. You should have it in your notes because it's printable off the module. What I want to do is take a look at this probability guy here. This thing falls off really fast, especially if the well is deep. If it goes to infinity, it falls off infinitely fast, and there's no penetration. So if I have a fairly deep well, and if I'm looking preferably at the ground state would be best, so that there's the effect of a very large well, then what does this thing differ than what I have with the infinite well? Well, what it kind of looks like is that it's made the well bigger. It's like it effectively increased the length of the well. So as an approximation, maybe what we could do is just use the formula for the energy levels of the infinite well, but put in a new L, a new width, and get an approximation. If you do that, that's called approximating a finite well with an infinite well. And that's the next set of notes in the textbook. So I sent you out some notes. Talk a little bit about this guy. So you have a finite well. And if you work the regions, where I call this region 1, this region 2, and this region 3. Then on this side, you have this wave function. Now this may look funny to you because it says e to the alpha x. Doesn't this go to infinity? No. Because x is what type of number over here? Positive or negative?
Negative.
Negative. So when you put a negative number here, this makes this a negative exponent. Over here, x is a positive number. So to make this go to 0, this has to have a negative in front of it. In both cases, they are decreasing exponentials. And furthermore, you can find the alpha from Schrodinger's equation. The square of it is this. So if this U naught is much larger than this E, this alpha is very big and this thing decays very quickly. Now, the question is, where to decide on the new width of the box? And the answer is you can choose any dang thing you want, pretty much. But what you want is to choose someplace where there's not much probability left. So if you go back to our graph earlier, it drops off pretty fast. And in this region, it's falling off as e to the minus 2 alpha x. The 2 comes because you square the wave function. So if you were to make x here, in essence, be like alpha, you would have 1 over e squared. And that would be the probability drop-off from what it was here. Because we're going to connect it with a constant that provides continuity. Well, that turns out to be about 13% of whatever was here. So it's already dropped off quite a bit. That's what's chosen. Is it the only choice? No, it's not the only choice. You chose anything you want. But it's always chosen that what you do is choose an x that's 1 over this constant. so that the wave function drops as 1 over E, therefore the probability drops as 1 over E squared. You could have made it 2 times that. You could have made it 3 times that. Generally, they choose 1 times that. So that's what the book was trying to get at. And they have a name for this. It's called the penetration depth. They give it its own symbol in the book, delta. So it is a place where the wave function drops off by an amount 1 over E. Now, in our case, that delta depends, of course, on the U naught. But here's the tricky thing, and I'll get back to it in a minute. It also depends on the energy of the particle. So it's not a constant. All right? We're looking for the energy, and yet the thing that we're putting into the formula depends on the energy. Now, if V is very small and you can ignore that, then it would be a constant. And I know U naught in the problem, and I'd be done. But it's not a constant. It depends on the energy, and I don't know the energy. Now, what's done is that we take this guy here, which, by the way, is missing a delta up here. We take that delta, and we say, hey, look, with my well, I'm not going to call its length here L. I'm going to say that it extends a distance delta out this way, and it extends a distance delta out that way. So now it's L plus the delta, so it's L plus 2 delta. And I'm going to stick that in the particle in a box formula that you're supposed to know by heart by now. And that's where he gets this formula, in the textbook. So he's got hc squared, that's just the normal particle in a box. He's got the m squared for the level, so that this is best approximating for the ground state when it is warm. I don't have L squared anymore, I have L plus 2 delta and squared. Now that equation looks really simple, and if this was a constant, it would be simple. But that's not a constant. That thing there has in it E. So you have E on this side, you have E on that side. This equation cannot be worked by hand. So how does one work it? Well, you can assume E is 0 and work it. Or you can write this into a spreadsheet or with a pocket calculator and go through what's called an iterative approach. First, you say, well, I'll assume E is 0. I'll assume U is much bigger than E. And I'll work the problem. And I'll get a value of E. Then I'll take that value of E, plug it back and calculate a new delta, and calculate a new E. Then I'll take that E, plug it back in, calculate a new delta, calculate a new E. And when I don't see the E changing, I have found the answer. Now the question is, how many times am I going to have to do that by hand? Is it 3? That doesn't sound too bad. 34,000? That might not be a good idea. Okay. So likewise, what did I do? Well, I gave you some answers in the notes. I'm going to show you where I got my note answers. I gave you these answers based on particular wells. So the first one, this was from his book. He doesn't show the calculations. It says, estimate the ground state of an electron confined to a potential well of width 0.2 nanometers and height 100 electron volts. Okay. So I sat down with a spreadsheet, and I put up here first, it says 100 electron volts, okay? So we'll make that 100. It says the width of the well is 0.2 nanometers. Got that. Energy. My first guess would be an energy of 0. There's my delta that's computed. 0.0195 or 0.195 angstroms. And it suggests that the energy should be 6.582. If you look in my first column, that's where I got those numbers from. Now I'm going to take that number and put it into my spreadsheet and do the process over again. So go up here, 6.582. I get a new delta. I get a new energy. Look at that. It didn't change a whole lot. 658 became 651. 7 parts of 658. It's pretty close. Why? It was a very deep well. 100 electron volts high, and I'm only about 6.5 off the bottom. So that's like me telling you, I'm not going to ask you to jump to the moon. I'm just going to ask you to jump over 5 houses. It's not like I'm asking the impossible. Well, you damn near are. Okay, it's pretty close. 50 feet might as well be 5,000 feet. Same thing the way the electron's thinking here. Now you take the 6.508 and you plug it in and do it again. 6.509. Now it didn't even hardly change. It only changed 1 part in 6,508. You take 6.509. Didn't even change. Done. That's the answer. So if the well is fairly deep, the number of iterations to be done by a pocket calculator are not many. This is basically the question that I asked you to be done here. Approximate the energy of an electron in the third excited state. So now you're going to have to account for the fact that you got to take everything I did and you're going to have to multiply it by 4 squared, right? 16. If you had a finite square well, the height was 3.6 and the width was 0.25 nanometers. And I can do it with a pocket calculator. You would not find it as easy to do that exact solution method with a pocket calculator. It has a lot of square roots and a lot of trigonometric functions in it. So it's a way to take what you know and effectively solve a problem that you can't solve exactly by using a spreadsheet or other computerized tool to get a real-world answer to solve a real-world problem. If you were an ABAT, they'd be saying that you are learning engineering tools and design criteria, whatever. All right? It's called solving problems. It makes such a big deal out of simple things.
What is the physical significance of the width of the well?
The width of the well, as you narrow the well, changes the spacing of the energy levels. So what I was going to look at right here. The effect of making the well finite, in essence, makes this bigger. That does what to the energy levels?
Makes it smaller.
Makes them smaller. So as you make the well wider, and you're not having these massive interactions at the corners, the effect of that is to drop the energy levels so that they're closer together and that they're deeper. All right? To make that, on the other hand, to go to 0, is to make those energy levels go up. So how would I change something like that? Well, I can do a lot of things. In an electrical engineering standpoint, I can dope it. That's what doping does. It changes the crystal nature, it changes the forces, which changes the potential. If I change the potential, I change the energy values. So if I change the energy level values, I change the photons that it will give off or accept. So I can change it from a blue light emitter to a red light emitter to a green light emitter to an infrared detector to an ultraviolet detector. Called band gap engineering. We build the project to what we want. God only gives us so many atoms. We can mix them any dang way we want. We understand quantum mechanics. Before they understood quantum mechanics, they had almost no control. You had metal, you had an insulator, and that's it. Modern electronics is because we learned through quantum mechanics how to adjust these properties tremendously. By just changing these wells, we can exponentially change probabilities. And that has huge things. Conductivity can be changed by 40 orders of magnitude in electrical engineering setting. 40 orders of magnitude. Think about that. From a conductor to a pure resistor, 40 orders of magnitude is standard in modern engineering. That's why we have so much power. Now, the next section after this also has electrical engineering applications. What we talked about there is barriers. So, in this case, you're not trapped. Why are you not trapped? Well, you could be, for instance, an electron ejected into the collector or emitter side, and this barrier, which will not be infinite in this case, but we're going to start with the simplest infinite case, be some finite section like this, represents the base of the transistor. This is how we will build, for instance, amplification. Also how we build fast switching for digital circuitry. By changing that potential, changing the width, we can dramatically change the probability that something coming in can get through that barrier. And in particular, something coming in with an energy that's too low to fly over the barrier. Classically, if you run in and you can't jump as high as the barrier, you don't get through. Not true for waves, though. Even in classical physics, for a wave that comes in, it has the ability to decay exponentially into the other thing and then reappear as a moving wave. We can tunnel through it. Now this is really cool. I mean, that basically says that because you are a wave, if you were to bang back and forth on the wall, there is a finite probability that you would disappear and appear on the other side of the wall. It may seem like it's difficult, but that's how alpha decay occurs. If you have uranium, for instance, or if you have an americium source, they bang back and forth, back, 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 back. But they bang on that wall. They really take this, try again attitude to the extreme. They hit it maybe 10 to 22nd times a second. Then over, say, 25,000 years, so multiply the number of seconds in 25,000 years times probably hitting it 10 to the 20th time, they eventually have a 50% chance they get on the other side. Okay. You probably don't want to leave this room by this method, but the fact of the matter is you have a finite probability if you were to ram into the wall back and forth, from one side of the wall back and forth, you could eventually pop to the other side and get out. So that's the type of problem we want to work with a barrier. Now, how do we work the problem with a barrier? Well, one is you got to do math. But even without math, I bet you I can draw the wave function for this problem. So one thing they can ask you is, don't do the math, just draw me the wave function out here and out here and explain to me what happens. So let's do that. So here's my wave function psi, b, whichever one you want, and then there's some big potential. On this side, it's wiggling. Why is it wiggling? Well, it has energy. Some E, maybe this much E. And the potential here is 0. So this difference between your total energy and your potential, what's that energy called? What is E minus U called?
Kinetic.
Huh?
Kinetic.
Kinetic. Okay, and what's kinetic equal? So that's K. So K is greater than 0 out here. All right, and what's K equal to if we're doing classical physics?
1/2 mv squared.
Huh?
1/2 mv squared.
1/2 mv squared is fine, but we don't like to work in V. We work in what instead?
P squared over M.
Huh?
There's a p squared over 2a. And I said we work in p's.
Yeah, we like that P stuff. So we prefer P squared over 2M. So that means that P squared is greater than 0. So P could be plus, P could be minus because it could be bouncing. So P could be plus, it's going this way. P could be minus, it's going that way because it hit the wall and bounced back like a baseball. All right? And both of those will actually exist simultaneously. You'll have wave functions going this way and wave functions going in the opposite direction that have been reflected off this barrier. It's one of the things we want to calculate, the reflection coefficient. The probability that if this particle comes in, that it's reflected. This is exactly the same math that's required for electromagnetic theory for E and M people. For for electrical engineers, calculating, for instance, sending an electromagnetic wave down in a cable television set and determining the percent of the power that's actually absorbed by the set versus the amount that's reflected back to the cable company. And you have to adjust your cable appropriately to maximize that power transfer. Why is it the same? Because it's a wave. And all waves have the same property. I don't care if it's a probability wave in quantum mechanics or it's an electromagnetic wave in electronics. It is the same math and the same physics required in both courses. So you need to learn to get double credit when you do your studying because you have to take both courses. You only have so much time to study. So this K means this P is real. This P is real. P is H over lambda. That lambda is real. So it has a wavelength. So it's a wavy thing of some sort. All right. I'll draw a wavy thing of some sort. Now, what thing's a wave that I like? I kind of like sines and cosines. A wave, something like this. And if I've drawn this right, this thing should have some wavelength. Related to P. Now, then get to my next place. I guess we got to stop. But then here, there's U, there's E. So what's K? Plus or minus?
Minus.
Minus. How do you get a minus when you have a P squared? What's squared gives a negative number?
Imaginaries.
Imaginary. So it's an imaginary wavelength. It doesn't wiggle. So this thing's got to go something like this. So that's the solution to the wave function. Square that, you have the solution to the probability function. Okay? Learn to be able to solve problems without jumping into math. Go don't do the math too, but you should be able to graph well. See you guys on Wednesday.
I'll see you later.